The arrow of time, I think, really consists of several distinct puzzles, and what these puzzles are at the technical level in detail depends completely on the theory that you're working in. Okay, and in particular, we tend to focus very much on the problem of somehow explaining why the universe started with low entropy initial conditions. But whether that's actually the problem that we need to solve depends completely on the theoretical framework. And I'll give you one example of an admittedly not by any means complete theory, but a framework in which this is clearly not the question that we have to worry about. So I completely agree with one of the philosophers, I think it was, who emphasized that in order to decide whether there is a problem, to say that the arrow of time is a problem, we first have to have a theory. And then that problem will show up as a prediction of that theory that conflicts with the data. And I think that really helps sort out what the technical problems are that we need to solve, which will have to do with that theory. So, but that doesn't mean, of course, that the arrow of time as a whole isn't something that we should obsess about, because it does smell like something that's going to be an interesting test for almost any cosmological theory that's sufficiently complete that we can even talk about this question. So let me first start by giving you a very simple model. Again, this is not by any means an attractive theory, but it's a framework in which we'll be able to see right away that the arrow of time is not just the problem of low entropy initial conditions, although in this example that will be one of the things that need to be explained or put in by hand. So here's my model. I'm going to have a Big Bang right here. I'm going to try to avoid the dreaded Penrose diagrams for people who are not familiar with them. So time does go up, but I'm going to have a closed universe which has a Big Bang and a big crunch, and this circle here shows the size of the universe at various different times. And then it recollapses. Okay. So what do we need in order to, be able to live here somewhere and say there is an arrow of time, there's an entropy which looks like it was lower in the past and is currently increasing? Okay, well, we need a bunch of different things. Okay. One thing that we need is indeed the usual obsession that we have, the initial conditions. So I'm going to write down a theory which is very ad hoc, which solves the arrow of time problems by just positing such a theory. Okay, so I'm imagining that there is some insight I had from, I don't know, quantum gravity that taught me that actually the initial conditions start with very low entropy. In other words, the entropy on this early time slice here is much, much less than, say, the thermal entropy of radiation that you could have had with the same density of matter on here. Okay, but that's not enough. Okay, another thing that I need to be that has to be true, and this I think is often overlooked, for there to be an arrow of time, it's not just enough to have little entropy to start with. You also have to have a high ceiling. You have to be able to go up to really high entropy so that there is some gradient that's possible for a really long time, right? So, for example, with natural assumptions about this closed universe, well, what are the natural scales in physics? It's the Planck scale. Yeah, a natural closed universe has a degree of curvature down here, which makes it be so that this recollapse occurs at a time of order the Planck time after the Big Bang, and the universe never gets bigger than about a few Planck lengths across. And then the holographic principle immediately tells us that the amount of entropy in this universe is of order a few bits at most. So in that universe, even if you started with 0 entropy, there isn't going to be much of an arrow of time. And it sounds kind of stupid, but it shows that the arrow of time really is a multifaceted problem. There's no point trying to explain the initial conditions if you're not going to be able to explain how the universe got so large. Okay, and how the universe got large, again, that's a multifaceted problem. One thing you need to make sure is that the curvature here is low. Okay, so I need it to be true that the radius of, let's say that this is one Planck time. Okay, so I need it to be true that the universe at 1 Planck time is much, much larger than 1 Planck length. That's basically the statement that the curvature in the universe is low. And that's, I have to put in a very large number. I'm going to do that for the time being by hand. So the radius right here is much, much greater than the Planck length. Okay. That will ensure that the universe also gets very old and big before it starts recollapsing. Okay. And I need to make sure yet another thing, which I haven't talked about, which is that the cosmological constant is small. So in my theory, I'm just going to start by setting it equal to 0. If the cosmological constant was naturally large, positive or negative, but of order the Planck density, so vacuum energy density was as high as a naive calculation from the standard model would tell us it should be, then again, the universe would effectively never become large enough to contain more than a few bits of information. If the vacuum energy is small, that's because, again, it will recollapse on a time scale of order 1 over square root of the absolute value of lambda. So if this is 1, then that's the Planck time. And if lambda was positive, then it would expand so rapidly that horizons form, a de Sitter horizon forms. Every region in the universe is essentially like living in a box, and the size of the box is a few Planck lengths, and the entropy or maximum information in the box is a few bits. So another one of those problems that you need to solve is why is lambda so small? That's the cosmological constant problem. If you don't solve that problem, again, you don't have a high enough ceiling for there to be an arrow of time. So in my model, I'm going to just write down a model where everything here is solved by hand. Okay, so let me review my model. It's not a very attractive theory. Your prior for it would probably be quite low, but it's a theory. Sorry. So here's some potential for the various particles and fields that we see. Let's call them phi. And we sit down here, and the potential energy down here is exactly 0. So that's the statement, that lambda is equal to 0. And my theory of initial conditions has to solve both of these problems. It has to solve both the problem that the universe is flat, almost flat, so that it can become big and old and doesn't recollapse right away. And it also has to solve the problem of initial conditions being such that the initial entropy is very small. So I can put that in by hand. Again, it's not a very attractive theory, but I think now in this framework I don't have an arrow of time problem. Okay, if I could actually come up with an attractive, coherent, detailed theory that did all of this, we might be pretty happy. Okay, but we can at least, and this is where I see inflation coming in. I would never claim that inflation somehow explains why the universe started with low entropy. I think that that is just nonsense. But on the other hand, I think that it's unfair to pin all these problems on inflation somehow. I mean, it's something that the theory doesn't have much to say about. What it has something to say about is at least one of the aspects of this problem, namely this one here. Why was the universe relatively flat at early times? That, I think, by most standards, physicists would say that it's less fine-tuning, it's more elegant. I would put a higher prior on a theory which has a period of slow roll inflation. There's a bit of tuning involved here, obviously, that can take a naturally curved initial condition to one where you have a great degree of flatness. That looks better to most physicists than saying that you have to do fine-tuning down here at the degree of 10 to the minus 30 or something like that to put in the flatness by hand. And that's the place where inflation, I think, offers us some degree of improvement, but it doesn't solve this problem.
So, Raphael,
yeah.
But what if you need more tuning to start inflation? So then you have to work out trade.
Yeah. So my point is just that I have to start here in any case. So qualitatively, right now my theory has a box here that says the initial conditions require that the initial entropy is extremely small. Okay? And whether or not I have inflation, that problem is there. And I don't think it matters very much whether I can allow the initial entropy to be 1,000 or 100, because it's already clear that we have that problem, right? We could start at nucleosynthesis and, as I like this, you could have complained that nucleosynthesis is a bad theory because the initial entropy is smaller at the beginning of it than at the end, so aren't we worsening this problem? But clearly there's some qualitative problem going on where it's not a question of how much less than the current entropy the initial entropy is. It's just a ridiculously large amount less, and there's some explanation needed.
So you have to, your agnosticism about that is critical to your argument.
Yeah, so let's,
Introduce a new piece
yeah.
and increase the burden on the first box there. Some might say it's not clear that you benefit.
Well, again, but I think by the same argument you could say that we should criticize Big Bang nucleosynthesis.
No, because you know,
We should start the universe a second ago.
understand the arrow of time.
Sorry?
No one's claiming that's helping us understand the arrow of time.
Well, I also said that I think it's absurd to claim that inflation helps us understand this part of the arrow of time problem. What I'm pointing out is that there are other parts which it does help solve, but nobody usually discusses them as part of the arrow of time problem.
Just very quickly, in your model, does your black box also say the entropy is small at the final moment?
That's my black box. Oh, there.
Yes.
No, it's totally asymmetric, so it's very ugly.
You put in the arrow of time.
Yeah, look, so what? Yeah,
Okay,
I put it in.
put in the
Yeah,
arrow of time.
yeah. No, it's not very attractive.
I thought you said you solved the arrow.
I told you that the prior for this theory is very small. I can solve anything by just, making it explicitly part of the theory. That's all I'm saying. The reason that I'm writing down this model is not to give you, to convince you that I figured out a great way to solve the arrow of time problem that should make us happy and go home, but as a way of illustrating what the various facets of the problem are, including some that tend to get overlooked. Now, I think I'm going to have to defer other questions probably so that I can make sure that I get where I want to get. So far, notice that I also simply declared that lambda is equal to 0. That was another totally ad hoc thing that I did, which, for a long time, we tend to do in a lot of theories, actually. But this is, so this is still ad hoc, okay? And this thing here that I start with entropy extremely small, let's say order 1 at the beginning, is still completely ad hoc. So again, I want to emphasize this model is not a very interesting theory. Okay, but it's worse because we know that this is not just ad hoc, it's also wrong empirically. Okay, and that's actually quite important. Okay, it turns out that the character of the arrow of time problem changes considerably when you take into account that the observed cosmological constant is actually positive and not 0. And this is probably one point on which Andy and I agree pretty strongly. It completely changes the game, though maybe we don't agree completely in the ways in which it does, but it's extremely important to take into account that this is wrong. Okay? And you can see immediately that it changes the game because you might think that all I need to do at this point to correct for the fact that lambda is actually, I don't know, 1.5 times 10 to the minus 123 in Planck units and not 0, okay, is to move up this entire potential by this tiny amount, 1.5 times 10 to the minus 123, so that now the minimum of the potential is, that amount above 0, and so that would be the cosmological constant that we see in the data. And this, of course, is still just as ad hoc as before. It's no better or worse in that respect. But it doesn't work anymore. That tiny modification makes sure that it doesn't actually work anymore. And this is loosely related to these beautiful graphs that Andy was showing, where you no longer go out to infinity, you come back and go around. There's a big difference between lambda equals 0 and any, however tiny, non-zero value. What happens, okay, is that if you have a value like ours, and the universe is as flat as ours, and let me, for the sake of just drawing pretty pictures, still assume that the universe is spatially closed. But what happens is that at some time before recollapse starts, in my new model, the universe goes from decelerating its expansion to accelerating its expansion. In our universe, it happened about halfway through, up to the current age of the universe, that acceleration set in. And as a result, you get, at late times, you don't get a collapse anymore. And instead, what you get is an infinitely large universe called de Sitter space, which grows at an exponential rate as a function of time. So the volume grows, doubles every fixed amount of time. And not only is this universe infinitely large, we also know from calculations by Hawking and Gibbons that this universe maintains a constant temperature at late times. The temperature does not drop down to zero due to effects that are closely related to the Hawking evaporation of black holes. Okay. So you have a thermal background in this universe. This temperature is incredibly small for a value of the cosmological constant like this. It's basically given by the square root of this in Planck units. The typical quantum has a size of billions of light years. It's a very low temperature, but it means there are going to be fluctuations, including very rare Boltzmann-type fluctuations that fluctuate out big objects if you wait long enough. And you can wait as long as you like because it's infinite. There's infinite space and time, and so you will produce infinitely many things by fluctuations, including observers. Most of those observers do not see what we see. They don't see all this other stuff. The cheapest fluctuation is just to make this famous Boltzmann brain that thinks it sees something. And so, in a sense, the honest folks who live down here, like us, are infinitely outnumbered by the infinitely many brains that pop out of the thermal radiation up here. Okay, that's the zeroth order argument for why this doesn't work. And they are, sorry? They are dishonest. Boltzmann brains, they're vicious.
Speak for yourself.
I was also a little bit dishonest because the first order approximation to this discussion is actually that you can't even tell whether there are more Boltzmann brains or ordinary observers because both of them, both types of observers, there are also regions here where galaxies get fluctuated out. And because both types of things happen infinitely many times over and over, you have a problem of trying to compute probabilities, Boltzmann brain over ordinary observer, which look like this. So really the reason that this doesn't work anymore is that the probabilities aren't even well defined anymore. Okay. But in any case, you see that already something pretty dramatic has happened as a result of just shifting up the cosmological constant to a positive value. Okay. And so let's take a step back and reconsider what the problems are that we are getting from what we know about the energy density of the vacuum. And so I think maybe now I can just erase this. There are two problems. Okay, one is just again the old cosmological constant problem. If you compute typical contributions to the energy of the vacuum using well-tested stuff like the Standard Model, you find that they are all at least 60 orders of magnitude larger, if you assume supersymmetry, than the observed value. Now they could cancel, they become positive and negative, but it seems ridiculous to assume that they just do so by pure luck. And so we need to explain the cosmological constant problem. Why is the observed value of lambda so much less than the natural value? Okay, and then the second problem has to do with the fact, not really what the magnitude of the cosmological constant is that we observe, but as I already pointed out, the fact that it's positive has really important implications. And one of those implications is the one we just discovered. Even in my very primitive model that had only one vacuum, if this vacuum is at positive vacuum energy, you get eternal inflation. You get something like the Sitter space, which keeps inflating forever. And you get this problem of infinities appearing in any attempts to compute probabilities. And this is called the measure problem. How do you know that it's unlikely to win the lottery if there are infinitely many places where you win the lottery and infinitely many where you don't? It sounds kind of stupid. We know how likely it is to win the lottery, but once you start asking questions about cosmological observations, you get very, very confused. And really, it does undermine our understanding of how we compute any kind of probability. So let's take a step away, because otherwise I don't really know how to motivate the multiverse and the measure proposals that have been discussed. Let's take a step away from the arrow of time for a minute and just worry about these two problems for a second. Okay? They are things to worry about independently of the arrow of time. I spent several years worrying about them without thinking much about the error of time. And let me briefly just give you the state of at least my thinking on these problems. So the cosmological constant problem, the first one here, well, I would love to hear about other approaches. I don't know of any solution currently other than the landscape of string theory. Okay, which is something that I find it kind of ironic that it took so long to discover this, because we tried coming up with solutions to the cosmological constant problem in frameworks where we had a lot more freedom and failed. And it was somehow string theory forcing us to think about the fact that it really has a multidimensional landscape. You get to choose what you do so let me briefly just say where the landscape comes from. So here's our 3+1 dimensional world, which we see and which is big. And in string theory, you have what used to be an embarrassment of 6 extra dimensions, which you somehow have to curl up. Now, which way they curl up depends on what sort of matter you throw in there. Okay? And the combinatorics of how much matter you can throw in there has to do with how many handles your internal space has. And it just so turns out, mathematicians tell us, that there are hundreds of handles on typical 6-dimensional compact manifolds. And if for every one of those handles I get to do 10 different things, like wrap 0 to 9 d-branes on it, which are, again, objects just handed to us by the theory, well, I get something like 10 to the hundreds of possibilities. For some reason, 500 gets mentioned a lot, but it's not really that we understand it to that level of precision. So it's really quite an order of error here. But the point is not exactly what this number is. The point is just that it's very, very large. There's a lot of ways of making a 3+1 dimensional world. About half of these vacua you would expect accidentally have positive energy. And if you throw enough darts, some of them are going to land pretty close to 0. There are going to be accidental cancellations in some of these vacua. Those are the regions where there's room for a lot of information. Again, by these holographic arguments, you need a small cosmological constant to have a lot of causally connected space. And so on quite general grounds, you would expect observers to live in regions where lambda is much less than 1. If you want to get the 10 to the minus 123 out, you have to put a little more information in, like when you want these observers to live, for example. But that works pretty well. And it leads, of course, because there's now not just one, but many vacua with positive energy, you still have this situation of eternal inflation. So it's just enriched now by the fact that this infinitely large universe that you're making has different effective low energy physics going on in different places depending on which kind of compactification occurred in these different regions of the universe, which way you made your 3-dimensional space. Okay. That's kind of connected to this problem. Okay. Again, eternal inflation is kind of a problem in its own right, but it becomes particularly important to solve the measure problem if you want to make predictions in the landscape of string theory. And the measure proposal that I've been focusing on is to essentially reject completely this global picture and say that all that really matters is what any one observer can see. Now, I'm not saying that only one thing could possibly happen. What I mean by this is that we should not worry about correlations between this point and that point, which is in nobody's past light cone. So these are really Penrose diagrams. This is future infinity, if you will. And the statement that there are horizons, that you live in a box, is the statement that there are places out there from which light cannot reach you because it can't travel to you fast enough. So we should not worry about correlations between 2 points like this that nobody can ever measure. This is a lesson that came out of black hole physics. It seems like we have to do this anyway, so this is really just an attempt to get more mileage out of something that we have to do anyway. And when you do this, when you basically trade this geometric multiverse, which looks like this infinitely large, infinitely redundant space-time in which things happen over and over and over again, you're trading that for this finite size causal patch in which different things might happen. So you're really trading the multiverse for the many worlds. Okay, there are different histories that can happen here, and in fact you can understand decoherence quite nicely, even without referring to specific observers, by just tracing over degrees of freedom that leave the causal patch, and that will generate different branching histories. So if you use the causal patch to compute probability distributions, now the number of times things happen in the causal patch, expected number of times, is going to be finite. You can take these ratios, you can say that the probability to measure different values of the cosmological constant is this and that. And you find, for example, for the cosmological constant, a very good agreement with the data. So if this is the data point, you get a curve like this over log lambda. Okay. So it works pretty well, but now let's go back to our original motivation here. We were worried about the error of time. Okay. So does this have anything to say about the error of time? And the interesting thing that happens, and this is sort of the punchline here, it's quite a lengthy calculation, but the condition for solving the error of time problem is now not that you start with low entropy initial conditions. That is almost completely irrelevant. You can start with extremely high entropy initial conditions. For example, you could start in the vacuum in the landscape that has the smallest positive cosmological constants, is some de Sitter space with enormously large radius and enormously large entropy, much larger than the entropy in the visible universe today. You could do that, but what turns out to be necessary in order to solve the error of time problem is that all the vacua in the landscape decay faster than the time that it takes to produce Boltzmann brains. So for every vacuum, the following relation has to be true. So now this is no longer some mysterious thing about some theory of initial condition that we can't even envisage. This is something that in principle, if you understood the landscape of string theory, you could just calculate. If this either is or isn't true, well, okay, you do have to decide how hard it is to produce Boltzmann brains, but our biology friends are going to solve this problem for us. And then it's so what I want to stress here is not that we've solved all problems, but that the nature of the problem becomes completely different. I wish I had time to explain to you how these two statements arise, but I don't. But again, it doesn't matter what the entropy is that you start the universe with. On the other hand, it does matter that this be true for all the vacua. So it's a completely different condition. Okay, and so I think the general lesson here is, again, that you have to discuss the error of time in the context of a specific theory. And I'm pretty hopeful that we can get to a point where this might become a reasonable solution to the problem. But I should emphasize that even if I now allow high entropy initial conditions, the entire framework still has a huge amount of time asymmetry built into it. I mean, I am starting somewhere and worrying about how I'm starting there and not worrying about how I'm ending up. So I'm treating the whole thing in a very time asymmetric way. And I'm also requiring, for example, that there are vacua at which you end up in future singularities. So vacua with negative cosmological constant, which are almost certainly there in string theory. But the way that those are treated is sort of sinks as endpoints of time. And so, again, this isn't yet completely removed from these sort of ad hoc assumptions that we still build into our cosmological theories, but I think it changes the nature of the question. Thank you.